we have that the tangent of phi is opposite over adjacent. The opposite side to phi is this side over here, which has a length of VL0 minus VC0. So VL0 minus VC0. Over the adjacent side, which is this side, which has a length of VR0. So over VR0. But we know VL0 is equal to XLI0, and VC0 is XCI0, and VR0 is RI0. Well, from that we can see that we can factor out the current from the top and the bottom, leaving us with tangent of phi equals XL minus XC over R. Now we're done. Well, for this analysis part anyways. We have figured out the complete relationship between our applied voltage of a form V0 sine omega t plus phi and our current form I0 sine omega t. With an applied frequency, angular frequency of our voltage of omega, we found out that the amplitudes V0 and I0 are related to each other by this factor of Z, the impedance. The impedance then depends on the resistance, the capacitance, and the inductance, R, C, and L, and omega, the frequency, because these reactances depend on not only, the inductive reactance depends on not only the inductance, but the frequency, and the capacitive reactance depends on not only the capacitance, but also the frequency. So the frequencies are in there. That's the impedance that relates the amplitude of the voltage to the amplitude of the current. We find that the voltage leads the current by an amount phi, where phi is given by tan of phi equals XL minus XC over R. Where, let me just get back to a point I made before. If XL is larger than XC, this will be a positive number, and phi will be a positive angle. Essentially, the voltage across the inductor would be larger than and I had to erase part of that, sorry, the voltage across the capacitor, and the voltage would lead the voltage across the resistor, in other words, the current. However, if XL is less than XC, this would be negative, and phi would be negative, and the voltage across the power supply would lag the current. Well, the idea is that if the circuit is more inductive than capacitive, so to speak, if XL is larger than XC, the voltage leads the current. If the circuit is more capacitive than inductive, in other words, if XC is larger than XL, then the voltage will lag the current. In other words, if the inductor aspect of the circuit dominates, then the voltage leads. If the capacitor aspect dominates, the voltage lags. Well, that makes sense. That goes along with what we first learned about the inductor and the capacitor from the last lecture. Very good. Before we stick some numbers in here, there are a couple more things I want to do. Let's take a look at how much power this circuit uses. We've already talked about how to determine power in a circuit. We just have to take the voltage times the current. Let's figure out how much power is used in this circuit. As we've seen before, the power used by the circuit, by any circuit, is just the current times the voltage. But now, because we're looking at time-dependent quantities, both the current and the voltage are time-dependent. In this case, the current is I0 sine omega t, while the voltage is V0 sine omega t plus phi. Pulling out the I0 V0, that gives us the power is I0 V0 sine omega t times sine omega t plus phi. Well, let's see if we can simplify this somehow. Let's use the sine of a sum trigonometric identity. In other words, sine of A plus B. Sine of A plus B is sine A cos B plus cos A sine B. In other words, sine of omega t plus phi is sine omega t cos phi plus cos omega t sine phi. And then we have to multiply that by sine omega t and I0 V0. Let's pull that sine omega t in the parentheses, and we'll write this as I0 V0. Then sine times sine gives us sine squared omega t cos phi plus sine omega t cos omega t sine phi. This is a very complicated time dependence. this is very complicated. We've got a sine squared term over here, a sine omega t, cos omega t term over here. This is a very complicated time dependence. This gives us the instantaneous power. How much power is used at any particular time. If you wanted, you could put any time in here you wanted, some value for time, 3.27 seconds, and you could figure out how much power is being used at that instant. Typically, that's not as useful as what's the average power being used. This is oscillating with a frequency omega. How much power is used if you average over an entire cycle or over many cycles? What's the average power that's being used? For, say, a lamp or something in your house, if you plug it in your wall socket that has a frequency of 60 hertz, the amplitude, the voltage source is oscillating at 60 times per second. You don't really care how much energy your lamp is using at any instant, but how much energy is it going to use over the course of an hour or a day or a week or something like that? Usually average energies or average powers are more useful to us than instantaneous. So let's see if we can't figure out what's the average power. Well, I naught and V naught are constants. Phi is a constant. What we need to do is figure out what's the average of sine squared omega t and what's the average of sine omega t cos omega t. And then we can put those averages in there to figure out what the average power is. Sine omega t, we know, looks something like this. It starts at 0, it goes up and down, up and down. Cos omega t starts at 1, this is when t equals 0, and then goes down and down like that. Now let's look at sine squared. Here's sine. What does sine squared look like? Well, when sine is 0, what's sine squared? Sine squared is 0. When sine is 0, sine squared is 0. Sine is 0, 0, 0, 0. When sine is plus 1, what is sine squared? Well, plus 1 squared is 1. So sine squared is plus 1. When sine is negative 1, what's sine squared? What's negative 1 times negative 1? Plus 1. When sine is 1, sine squared is 1. When sine is negative 1, sine squared is negative 1. Well, all we need to do is kind of connect these with a nice smooth curve, and what it turns out, it looks like this. It looks like a sine wave that's half as tall, that's moved up so that the whole thing is on the t-axis and above. What's the average value of that? Well, it's oscillating from 0 to 1, 0, 1, 0, 1, 0, 1. It spends just as much time at 0 as it does at 1, so what's the average value? Right in the middle, 1/2. The average value of sine squared is 1/2. Very, very good. Now what about sine cos? What about the product of sine times cos? Well, let's try and do this the same way. Let's think about this. Well, at the beginning here, when t equals 0, sine is 0. So what is sine cos if sine is 0? It's 0. In the middle here, cos is 0. So what's sine cos if cos is 0? It's 0. Over here, sine is 0. So we know the product is 0. In the middle here, cos is 0. So the product is 0. Here, sine is 0. So we know 0. Here, cos is 0. So 0. Well, I think you can see 0, 0, 0. But it's not always 0. Let's look in between these. So in between here and here, sine is positive and cos is positive. So what is sine cos if both are positive? It has to be positive. So this is going to come up like that. Now over here, sine is positive. From the middle here to this line, sine is positive, but cos is negative. What is sine cos if sine is positive and cos is negative? It's got to be negative. So it's going to go like that. Now for the next section, sine is negative and cos is negative. What is sine cos if sine is negative and cos is negative? It's got to be positive. So it's going to come up here. And then what about here? Sine is negative, cos is positive. That's negative. And then sine positive, cos positive, positive. Sine positive, cos negative, negative, etc., etc. There we go. We end up with what looks like a sine wave, but it's now compressed this way. What's the average of that? In this case, we've got positive, negative, positive, negative, positive, negative. We have just as much positive as negative. What's the average? The average is 0. Very good. What did we end up with? The average of sine squared is 1/2, while the average of sine cos is 0. That leaves us with the average power is 1/2 I naught V naught cos omega t. Let me rewrite that and take a look at it. The average power then, which we can sometimes write as P sub AV for average, or we can put it into brackets. The average power is then 1/2 I naught V naught times cos phi. It's kind of a nice simplification. If we take that 2 and multiply it as the square root of 2 times the square root of 2, and write it then as I naught over root 2 times V naught over root 2, separating that out into the two parts, one under each one. But then what's I naught over root 2? It's I RMS. And what is V naught over root 2? It is V RMS. So we can write the average power as I RMS V RMS cos phi. This is a very nice, simple form. Let's think about this just for a second. Let's imagine phi is 0. Phi would be 0 when? That would be when the applied voltage is actually in phase with the current. I'll come back to that in just a second. Where phi is 0, we have V naught sine omega t and I naught sine omega t. The current and the voltage are in phase. In that case, cos 0 is 1, and we have P average is I RMS V RMS. First of all, notice it's a very, very simple form that looks exactly like the very standard form that we had for DC circuits. Except, in this case, we're talking about an average power used by an AC circuit. And rather than just the current and the voltage, we use the RMS current and the RMS voltage. This is, if phi is equal to 0, we end up with a very, very simple form that looks very much like what we had for the DC circuit. However, what if phi is not 0? If the voltage is out of phase with the current, either in front or behind, cos phi is a number less than 1. And whether phi is positive or negative, it's still going to be less than 1. In that case, the power used is reduced from just the product of I RMS V RMS. The circuit uses less power because of that factor of cos phi. Cos phi is actually referred to as the power factor, because it tells us how much that average power is reduced from just that simple form of I RMS V RMS. Very, very good. Now I'd like to get back to this idea of when is the current, or when are the current and the voltage in phase with each other. In other words, when is phi 0? Let's go back to that.